So last time we start discussing memory management. So remember, memory is not doing any processing, but memory is playing a critical role by speed up the access of data and instruction by your processor. So rather than accessing it from your secondary storage, like hard disk or SSD, accessing content from the memory is much faster for the processor. So that is the whole idea behind a memory. So therefore, your memory has currently running programs, maybe part of it, including the operating system. Again, not entire operating system, the essential, and the related data like documents and data, right? And each memory unit is a flip-flop or latch, okay? Right, so remember it's a hierarchy. You have the cache memory, L1, L2, and L3. Always your processor check the cache before checking the memory. And whenever it gets something from the memory, put it into the cache. Then we look at the way we understand the memory. So each memory unit has a memory address, and it can keep either 8-bit or multiple of 8 bits. Okay. So then we discuss about what is virtual memory. So when your program is running out of physical memory, it can think of part of the secondary storage as extension to the memory. But in reality, it is not memory, but it can look at it as a bigger storage or memory by swapping your memory pages to and from your main memory and secondary storage. So therefore, your programs can see bigger memory than actual memory. So when you, because it can see the memory as both your physical memory and the virtual memory. Okay. So sometimes we call it logical memory. Physical memory plus virtual memory, we call it virtual memory. Okay. Sorry, we call it logical memory. Right. So today we want to discuss about memory address translation. So remember, in reality, your computer has physical memory. Right? Physical memory. In my case, my computer has 8 GB of physical memory. So that is your actual memory. Right? Physical memory. But remember, computer can think of part of the hard disk as an extension to the memory. We call it virtual memory. Right? Virtual memory. So this is your physical memory. This is your virtual memory. Okay. So your computer programs or running programs can think of the memory as this big chunk. That is physical memory plus virtual memory. So it can think of like your memory is this big. And we call it logical memory. Logical memory. Okay. And there's a confusion in some, because some people use the word logical memory for this part as well. And also they call this entire thing as virtual memory as well. But in my discussion, I will stick with 3 words: physical memory, virtual memory. Together, I call it logical memory. So logical memory is what your programs are looking at. Your programs' views of memory. Your programs feel it like, see it like this much of memory is there. But in reality, this much of memory is there. That is your physical memory. That is your operating system's view. Because operating system must look at the reality. So therefore, now you can see that, remember, each memory location must have address. So this is physical memory. So physical memory must have address. That is what your operating system is looking at, because that is the real memory. But remember, programs look at it memory as this much, because it's consider both physical memory and virtual memory as logical memory. So therefore, what happens is we have 2 types of addresses. Physical memory address, that is the real memory address, and logical memory address. Logical memory address cover the entire memory space. Okay. So now you know the reason why do we have two concepts, physical memory address, that is actual hardware memory address, logical memory address, that is how your program look at the memory, which is not real, it's conceptual, but that is how your programs look at it. So the reason is most of the time, this physical memory is not good enough, big enough. So therefore, computer operating system play a trick with programs, showing the memory sort of exaggerated. Okay. So therefore, we need something called memory address translation, because your programs refer to logical memory, but in reality, we have only physical memory. So therefore, operating system need to do that translation from logical memory to the physical memory. Okay. And in some cases, physical memory to the logical memory, but most of the time, logical memory to the physical memory. So that is our topic for today. Needs usually A-level ICT students consider this topic as one of the hardest topic. So their hardest topics are for the entire A-level 2 years. One is this particular topic that I discussed today. And almost every year, or at least every other year, there's a question on this, because the examiner also know this is one of the hardest for the students. So therefore, he or she can control the marks. So some students consider another topic as one of the hardest, that is subnetting in networking, calculating subnetworks, their IP address ranges. So that is another, if you ask from students who are preparing for the A-level, so they will say, yes, that is a tough topic. So those are the two tough topics for most of the students. Not everyone, of course, once you understand, it's not a tough. Okay. And some students find it, even the programming also a little bit tough. That is, of course, if you are not very good at programming, or if your attitude is not that good. So those are the three topics. Okay. Memory address translation, in the networking, subnetting, and also programming. And some students find the logic circuits questions are also tough, like Carnot maps and so on. Anyway, we have already done that part. I hope now you guys are okay with that. So this is another such a milestone, hurdle, right? Challenge, understanding this. So therefore, if you have any question, ask. And I do this very slowly, because this is another milestone, right? So this is like a uphill again. So then, of course, again, we have plane where we can go fast. Right. So now you know we have physical memory, and there's something called virtual memory, which is not real, but we can think of, or the operating system can, or the actual programs can see it as part of the memory. So altogether, we call it logical memory. So programs think that memory is actually the logical memory, but in reality, it is physical memory. Okay. So then we need translation. So this is your physical memory, the actual memory in your RAM. This is your virtual memory, part of the hard disk or SSD. And your programs, running programs, look at it as something called logical memory. Basically, logical memory cover both physical memory and virtual memory. Okay. So therefore, obviously, the range of memory addresses in logical memory is bigger than range of memory addresses in physical memory, because you don't have separate memory addresses for the virtual memory. So then someone might say, okay, so then what? Let's do it like this. Say, let's take an example. Say memory address from 0 to 100 is my physical memory. This is just example. Say 100 to 150 is my virtual memory. So therefore, altogether we have 0 to 150 as logical memory addresses. So that is a very simple solution, right? Say 0 to 100. So I just took 100 as arbitrary value. Say, yeah, as example, say that is my physical memory. If my memory address is between 0 to 100, it's actually a memory address, physical memory address. But if it is between 100 to 150, it is actually you are referring to virtual memory address. Okay. So then this is your physical address range and this is your logical address range. So logical address range goes from 0 to 150. Okay. But this is not the way we do it. So that is one possible way of doing it. But in reality, this is not the way we do it. Right? So reality what happens is we have separate physical address with a format and another logical address format, which is not just extension to the physical address. For example, your physical address 100 or 120 can be logical address 350. Okay. Of course, we take it from as binary. Okay. So that means it's two different address. It's not just this range is extended to create the virtual memory. No, that is not the way computer do it. You have one particular concept called logical physical address with a specific format, and another concept called logical address with another format. And there's a mapping between your logical address to a physical address. And obviously, some logical addresses are not mapped to a physical address because that is part of the virtual memory. So there's no mapping right there. So that means that logical address has no physical address. Some logical addresses have a corresponding physical address, but some other logical addresses, they don't have a corresponding physical address because so those data is not really right now in the physical memory, it's in the virtual memory or it's in your secondary storage. Okay, right. So then the next question should be, if there are some logical addresses which has no corresponding physical address, so what is the use of that? What is the use of that? How do you use that content? Because your programs are referring to thinking that there's a memory address like this and there's a content. So how does your operating system access this data content? So how it is done is we have concept called page table of your physical memory. Okay, let's look at that diagram. Right. So your computer memory look at your physical memory as having set of frames. Set of frames. A frame is consist of range of addresses. Maybe this frame has 100 memory locate addresses, 100 physical memory addresses. Maybe this is another 100 memory addresses, another. So I just take 100 as an arbitrary value. Right? In physical memory, set of consecutive addresses are called frame. Frame 0, frame 1, frame 2, frame 3, and so on. Okay. And when your programs refer to logical address, so there also you have same size address ranges. Say this is 100 memory addresses. This is also then 100. If this is 150 memory addresses are considered as a frame, here also then 150 addresses are considered as a page. Here we call it frame. Right? Here we call it frames. And here we call it page. Page 1, page 2, page 3, page 4. Okay. And page size and frame size are the same. Because if frame refer to 100 memory addresses, your page must also refer to 100 memory addresses. Okay. So pages are concept for the logical memory. For pages, page is a concept used by your programs. Frame is a concept used by your OS to look at consecutive set of consecutive memory locations in physical memory. And you can clearly see that they are, because each frame and each page has the same size, definitely there must be more pages than frames. So you must have more frames than pages. If there are, sorry, there must be more pages than frames. If there are 50 frames, possibly there are 120 or 70 pages. Remember, each page size is same as frame size. So what is the reason? Because logical memory is bigger than physical memory. Right? Logical memory is bigger than physical memory. So therefore, if physical memory has 50 pages, sorry, 50 frames, your logical memory may have 70 frames, 70 pages. Okay. And some of these pages are mapped to a frame. That means that page is really in the physical memory. Some of the pages. Right. For example, maybe page, this content is here. That is page 0 is mapped to frame 3. But you can see that page 1 is not mapped. B content is not there. So the reason is actually the page that you refer by your programs as page 1 is in the virtual memory. It's not in the physical memory. So therefore, every page must be either in your physical memory or virtual memory. So B is not in a physical memory, rather it is in the virtual memory. So the page C is mapped to frame 5. So that is 5. Page D is not dark. Page D is also mapped. Page D is mapped to, or the page 3 is mapped to frame 8. But page 4, so page 4 is in the virtual memory. Page 5 is in the virtual memory. Then page 6 is mapped to frame 1. And page 7 is mapped to frame 4. And page 8, again in the virtual memory, it is not mapped. So therefore, there must be a mapping between page to frame. And operating system maintain that mapping table, we call it page table, or the operating system call it page table. So it has a page number, frame number. And there's a third field called valid bit. For example, page 0 is mapped to frame 3. You can see page 0 is mapped to frame 3 and it's a valid. Valid means it's a valid mapping. Valid mapping. That means that page has a valid frame. Then page 1 is not mapped here. So therefore page 1 we have, but there's no frame number. There's no frame number. Therefore valid bit is 0. Okay, valid bit is 0. Then page 2, which is mapped to frame 5. So therefore page 2 is mapped to frame 5 and the valid bit is 1. Now you should be able to understand it. For some pages, no frame number, that means valid bit is 0. For some pages, there is a corresponding frame number and then valid bit is 1. So valid bit 0 means those pages which are in the virtual memory. If valid bit is 1, there's a corresponding frame in the physical memory. Okay. And this is called page table, which is managed by your operating system. So then someone will ask, if a program want to access a particular memory, say memory in this page 5. Okay, page 5. And if you go to the page table and page 5 has no frame, so that means page 5 is actually in the virtual memory. So then how do you access it? How does your operating system or your compute access it? Because maybe a program need to access this. The memory address in page 5. Right, page 5. So then what the operating system does is, if there are any free frames, you can see there are some free frames. It can take this page or chunk of addresses to one of the frame. Maybe let's assume your operating system decide to take it to the F7. Now this particular page, we label it as F is in F7. So therefore now, once it take that from virtual memory to the physical memory, it needs to update this page table because operating system maintain this. So then the entry will be page 5 is mapped to frame 7 and valid bit is what? Now, a particular memory address in page 5 can be accessed physically because now a particular memory address, logical memory address in page 5 has a valid physical memory address in the frame 7. That is how it is done. Now assume by the time you want to access a particular page, all these are occupied. So that means your frames are all filled. Physical memory is all say fully filled. In that case, what your operating system does is it will take one of the frame to the virtual memory, one or few, depending on the requirement. So once it take that to the virtual memory, it needs to update the page table. For example, now it says, so this is H, page 7 is frame 4. Right, page 7 is frame 4. Once you take this to the virtual memory, it needs to delete this entry and say valid bit is 0. Now it has taken this particular frame to the virtual memory. Now this is free. But page table now has updated saying that it is not a valid, there's no frame because you took it there. Now that free frame can be used by maybe if you are interested in something else like page 7 or something. So then now you can, now you have space, you take this to the virtual memory and take maybe another frame to that particular area. So then you have to update that one also saying, okay, it is now valid and this is your frame. Right. So then there's a valid physical memory address for that logical memory address. So once you have valid page, valid frame for valid page, that means there's a valid logical physical address for valid physical logical address. If there's no valid frame, there is no valid physical address for a physical valid logical address. So in that kind of situation, that particular memory chunk must be taken to the frame, and then only the memory address translation can be done. Right. Any question up to this point? Any question up to this point? Of course, still we haven't done, but I explain you the purpose and the mechanism. Mechanism at high level only, not still we haven't look at the reality, but high level, the strategy. Okay. Right. So in summary, we have pages in logical memory, that is a conceptual view, frames in physical memory, page size is same as frame size, and the page table maintains page number to frame number mapping with valid bit 1. If there's no corresponding frame for a particular page, then the valid bit is 0. But that means that particular chunk is in the virtual memory. If you need to access a memory address in which is located in the virtual memory, it must be first taken to the frame, physical memory, and update the page table. And sometimes before that, maybe a frame has to go to the virtual memory as well. And then it's a valid, now you have a valid physical memory address for that logical memory address. Sometimes straight away there's a valid physical address for logical address. Sometimes after this swapping, then only there's a valid physical address for logical address. So one way or the other, ultimately, every logical address must have physical address. So that is called memory address translation. Okay. Memory address translation. Right. So in order to understand the memory address translation, you need to understand what is meant by offset. Like offset. So the concept of offset is there in both page and frame. Because page is when you look at it in the logical memory, frame is when you look at it in the physical memory. Remember, the page size and frame size are the same. So offset means, say, particular page or frame, because page and frame is pretty much the same. Just if it is, when you look at it from the logical memory, we call it page. When you look at it from the physical memory, you call it frame. Okay. So therefore, if you take a page or frame, maybe this is the zeroth content. So remember, in IT, the first content is called zeroth content. Second content is called first content, and so on. I know it's a headache. Right? So therefore, this is your not 1, 2, 3, 4, fifth content. This is your fourth content, because this is considered as zeroth content. Right? Even when you do programming, you will find that when we work with arrays, so this element is called zeroth element, not the first element. Then first element, second element, third element, fourth element. It's a big headache for humans, because we are humans. We used to say that this is first one, second one, third one, but in IT, computer science, most of the time, if in both hardware and software, the first element is called zeroth element, and so on. Right? So that is crazy, right? That is crazy. Because as humans, so when there's first child, we don't call it that is the zeroth child of the family. We call it is the first child. And in this, right? So this is the first bus in the morning. You don't say this is the zeroth bus in the morning. And you say this is the first row of the class. This is our first class. This is our second class. We don't start with zeroth class. But in memory addresses, arrays, especially memory address, storage related things, we start with 0. So there must be a reason. Anyone has idea about the reason, or at least guess it? Because those are the questions that you must have answers. Those are the questions that you must have answers if you want to build your confidence. So there are two ways you can study. You keep memorizing things without worrying about understanding. So that is hard working, hard way of passing exams. Maybe you can pass the exams, but I doubt whether you can do anything useful to the society. The second approach is you rely on understanding. So your study means understanding things. So that is smart studying, smart people. And their knowledge is very valuable. So their knowledge is very valuable because they do things, they build things, they engineer things. So they are the assets to the society. Right. So the main reason, or not the main reason, the reason is these are addresses. So you know that when we are having house addresses, so there's nothing called 0, right? So the second, say, Hill Street number 1, then Hill Street number 2. There's nothing called Hill Street number 0. But in memory addresses, we start with 0? The reason is we give each binary address. Right? Binary address. So when we have a binary address, it's a bit pattern. So maybe this is a bit pattern. This is a possible bit pattern if you have 3 bits for the address. Then this is another bit pattern. 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 This is another bit pattern, and this is your there's no other bit pattern. When you have 3 bits, we have 8 bit patterns, 2 to the power 3 bit patterns. 8. 1, 2, 3, 4, 5, 6, 7, 8. So remember, for the computer, each pattern is distinct thing. And we have pattern like this. So if you start with 1, so then we can call this 1, 2, 3, 4, 5, 6, 7. Then how do you call this? So there are 2 options. Either you call this something else, or maybe 9 or something, or you call it 0. Or else you ignore this. Okay, I don't need this bit pattern because we like to start with 1. So then when we have 8 addresses, you are wasting 1 address. Because in computer, everything is money. Right? You have memory, you have possibility of creating a memory address called 000, but if you don't use it, you are wasting. So therefore, computer engineers have decided, okay, let's call this 0. Because this is a memory pattern. We don't want to ignore that pattern. So that is why your memory addresses start with 0, 1, 2, 3, and so on. So remember arrays, of course, still you have not done programming. Arrays is another way of keeping data, like a variable, set of values in one variable. So there also we call it 0, 1, 2, 3, 4. Okay. So therefore, remember in IT, 0 is a valid bit pattern, though that means it's a valid address. So that is why we start with 0, then 1, 2, 3 in most of the time when it comes to IT. Okay. Right. So now we have concept called offset. Say this is a page, or you can think of it as a frame, because page and frame is identical, because a page must be able to go and fit into a frame. Okay. So remember, a page or frame has set of data, contents, maybe 10 contents. Content of 10 memory addresses considered as one page or one frame, or maybe content of 100 memory addresses, you consider it as one page. It depends on the way your operating system look at it and your resources. So then, once you know the page number or the frame number, so then you must know exactly which content you are referring to. So this page number may be having 10 memory contents. So then how do you refer to a particular memory content in that page? So we use concept called offset. So this is the 0th offset content. This is the first offset content, second offset, third, fourth, and so on. So therefore, if you know the page number and the offset, you know exactly what is the content in that memory. If it is logical memory address, you must know the page number and offset. If you are referring to the physical memory, you must know the frame number and offset. And page number can be different from frame number. But offset is same. Offset is same. Why? Because a page must fit into a frame. So therefore, page size is same as frame size. So therefore, the content is in the same order. So therefore, if it is the 7th offset in your page, in your frame also, it must be the 7th, it must be in the 7th offset. So therefore, when you do the mapping, page number may have a different frame number, but offset is going to be the same. Offset is not going to change, because assume the data is in the same order and they are of the same size. So therefore, when we map logical address to physical address, the offset part is not going to be same, not going to be different. But page number will be mapped to a different frame number. That is okay. That is obvious, right? For example, here, you can see page 3 is mapped to frame 8. Right? Page 3 is mapped to frame 8. Because that is depending on the available situations, it has mapping. It's just randomly taking available thing, and but page number and frame number can be different, but the offset is not going to be the same within that page or frame, because ultimately you are referring to a particular memory address. You are not in general referring to a page or frame. Okay. So remember, in the exam, you get some calculation questions in the second paper, part A, structured essay. So most of the time they give you a calculation question. Okay. So therefore, how do you calculate the number of offset entries? That is how many entries are there. That is your page size or frame size. Page size means the total capacity for the data, ignoring the address, divided by your physical word size. Word size means for a particular memory address, how many bytes are kept in your memory. So that means most of the time it is 1 byte. Every 1 byte you get a memory address. So then your page number of offset entries in the page is, or let's say frame is, say your the total memory size is, for the total page size, say 1024 byte. Say each memory location has take 1 byte. So then 1024 divided by 1. So that means if your page size or the frame size is 1024, number of offset entries is 1024, because every byte has an address. But say your word size is 2 byte. So that means every 2 byte has a memory address. Again, assume that it is 1024, 1 kilobyte. So then how many entries are there? 1024 divided by, say this is 2 byte. So you have 512 entries, because every 2 byte has an address. Okay. Then you need to represent this offset as a binary number. Right? Now you calculate number of offset entries, right? For example, if it is 1024 and physical word size is 2 byte, 1024 divided by 2, 512 entries. That means there are 512 possible entries. Now that 512 entries we need to represent using a binary number. So in order to represent 512 possible values of set entries, how many bits are needed if you want to represent using binary? So that is log 2 512, or which power of 2 is 512? Right. So obviously that is log 9. 2 to the power 9 is 512, because 2, 4, 8, 16, 32, 64, 128, 5, 128, and then 512. 2, 2, 2, 2, 2, 2, 2, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. 4, 8, 16, 32, 64, 128. But 2 to the power 0 is 2 to the power 1 is 2, 4, 8, 16, 32, 64, 128. Then 128 into 2, 256, and then 512. So if you have 512 entries, you need 9 bits. 9 bits. If you have 1024 entries, you need 10 bits. If you have 16 entries, you need 4 bits. If you have 32 entries, you need 5 bits to uniquely identify the offset. Okay. So that is in mathematically you call it log 2 number, but just how many power of which power of 2 is your number of offset entries. Right? Which power of 2 is the number of offset entries, because ultimately you need to represent it using binary. So basically what we need to calculate is how many bits are needed to represent, uniquely identify the offset number. Okay. So I told you this is a bit of calculation. Right. So now let's look at how to do the memory address translation. So memory address translation means given the logical memory address, you must be able to calculate the physical memory address. So given the logical memory address, calculating the physical memory address is called memory address translation. This is something your operating system does, but we must know how the operating system do it. Okay. So remember, logical memory address is what your programs look at it. Physical memory address is the actual memory address in your physical memory. So we can subdivide logical memory address into two parts called page number and offset. And physical memory address also we can subdivide into two parts called frame number and offset. And remember, the page size is same as frame size. So therefore, page go and fit into a frame. So therefore, if there are 100 entries in a page, there are 100 entries in the frame. And they just fit in like this: 0th entry fit into 0th entry, first entry fit into first entry, and 100th entry fit into 100th entry. So therefore, this offset is the same whether it's logical address or physical address. So therefore, if you know the logical memory address and if you know where the page and offset separation, when you calculate the physical memory address, the offset bits you can just copy. So if your offset bit pattern is 100111010, your offset bit in your physical memory address is also 100111010, because the offset is going to be the same because page size and frame size are the same. So that is first thing you need to understand. Right? So when you do the translation, if you know where the separation point is, just left hand is page number, right hand is offset number. In logical, in physical, left hand is frame number, right hand is offset number. If you are supposed to calculate the physical memory address, just copy the offset bit from logical memory address to the physical memory address. So then you need to convert the page number into frame number. So that is where you have the page translation table. The operating system keeps track of which page is mapped to which frame, right? Which page is mapped to which frame. So in the question, they will give you the page table. By looking at the page table, you can find what is the corresponding frame number for the page. So that you need to look at the table and write it. So then for this particular logical address, you have calculated the physical address. Simple as that. Okay. So that's it. That's it. So that is how we do memory address translation. So you must be able to explain every bit and piece of it, why you are doing like that. So that is what is meant by studying. Adhyayane karna. So then in Sri Lanka, only about 2-3% of the students study Adhyayane karna. The rest of the 98%, they memorize. Padam karna. ඒගොල්ලෝ කවුරු හරි කියනවා මෙහෙම කරන්න කියලා ඇයි කියලා දන්නේ නැහැ හේතුවක් මුකුත් දන්නේ නැහැ ඒගොල්ලෝ හේ කරනවා කැල්කියුලේටර් එකක් වගේ ඒක මීහරෙක්ට උනත් කරන්න පුළුවන් චුට්ටක් මතක තියෙනවා. Right, so this is how the things are done in big picture. Right, big picture. So you have the logical address, you need to calculate the physical address, you must know the separation, how many bits are for the page number, how many bits are for the offset in logical address, and how many bits are for the frame number, and how many bits are for the offset in physical. Of course, number of bits in the offset is going to be the same. So then you copy these set of bits to here, then consult the page table and find out for this particular page number, what is the frame number, and convert it to binary and write it there. So you got the physical address. Okay, you get the physical address. But the examiner can give you the question in a little bit fussy way, so that the examiner can check whether you really understand this concept in the big context. Okay. So this is another example, a much clear example actually. Say this is my logical address. Let's assume this is my logical address. Then let's assume you know the separation point. Okay, let's assume. So you want to calculate the physical address. So your first task is copy these bits to your physical address. Right, from this point onward. So if it is 0000 blah 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 and ultimately 100, so that is also the same 100, all are 0. So that is because the offset is not going to be different. So then take this if it is logical address, this must be the page number. So page number 10 or 2. 10 means 2. Page number 2 is mapped to, say this is my frame number 110. And valid bit says valid. So therefore 0010, you can map it to 110. And this is your logical address, this is your physical address. Right? This is your physical address. So that is how you do it. So they can give you the page table in different ways. Sometimes they will give it in binary format, sometimes they will give it in decimal format. So use your common sense. And always your physical address will be shorter than logical address. You know why? You know why? Either same size or physical address is small. Physical address can't be bigger. Right? So the reason is, anyway, this width is not going to be changed because that is offset. And remember, physical memory is smaller. So therefore, it has smaller number of frames. Logical memory is bigger because we consider logical virtual memory also as part of the logical memory. So therefore, for smaller size physical memory, there's a smaller number of frames. Because this is the frame number. And for larger logical memory, we have large number of pages. So therefore, page number is bigger than frame number. Bigger means bigger range. So therefore, if this need may be 4-bit, most of the time this need 4 or less than 4. When this is 4-bit, it can't be 5-bit. Because here we have less number of bits, less number of frames. Right? So the next question is, what happens, say you get a logical memory address. So then, of course, you can simply copy this part, right, to get the physical address. So when you go to the page table, let's assume it is something like 6. 6 means 110. 4 plus 2 is 6. Now assume this is 0110. 0110 means 6. So therefore, you go for the 6. And it says valid bit is 0. So that means now you can't do the translation. Because for this particular page, there is no corresponding frame. Your valid bit says 0. Right? I took 0110. That is 4 plus 2, 6. So in that kind of a situation, what happens? Your operating system will take that particular frame into the physical memory. Maybe some other frame need to go to the virtual memory, depending on the situation. Sometimes without another page going to the another frame going to the virtual memory, if there is a available frame, of course it can load it. So then this will be updated. This will be updated and this will be 1, and now it will have valid page frame number, and that frame number is used. So until that time, use delay the translation. Delay the translation. Because operating system stop converting the memory address, rather it do that memory swapping and then update the page table. And now it has a valid frame number. Now it does the memory address translation. So all those things the examiner have asked. Right? The examiner has asked. Okay. Okay. So let's do this. Right. So this example, this is a little bit tough example, but this cover everything. Okay. That is why we do take this. But your exam question sometimes is easier than this. Right. So let's assume this. Your logical address space is 4 GB. Address space means your programs look at the memory as 4 GB capacity. Okay. So that is what is meant by that. So it look at it as 4 GB. Okay. Logical memory. Physical address space is 64 megabyte. So I told you physical address is usually smaller. That is the real address, physical. Right? Physical address. That is your RAM. So assume it is 64 megabyte. And convert everything into same unit, preferably byte. Otherwise you mess it. Okay. So therefore this is 4 GB means 4 into, remember 2 to the power 10 is kilo. 2 to the power 20 is mega. 2 to the power 30 is giga. So therefore this is 2 to the power 30 byte. And this is 64 into kilo is 2 to the power 10, mega is 2 to the power 20. 2 to the power 20 byte. So your physical memory is 64 into 2 to the power 20 byte. Remember, we have the addresses also. So this capacity doesn't include the address. This is for the data capacity. So your addresses will be there, but this is for the content. It is 4 GB. Here for the content, again, you have the physical memory address, but memory address is not considered for the capacity. And page size. Remember, page size is same as frame size. Say, if this is my logical memory, we call it page. Physical memory, we call it frame. And page size and frame size is the same. And this is, right, this is 4 kilobyte. And therefore, this is also 4 kilobyte. And 4 kilobyte means 4 into 2 to the power. Sorry, this is, I made a mistake. This is 2 to the power 20. This is 2 to the power. Giga is 10 kilo mega giga, 2 to the power 30. Sorry, I made a mistake here, right? 2 to the power 30. This is mega, 2 to the power 20. Okay, so this is bigger. Right, so kilobyte means 2 to the power 10. And this is also, because page size is same as frame size. So if they give page size, you must know frame size is all the same. If the question says frame size, you must know that page size is the same. That is 4 into 2 to the power 10 bytes. Okay. So all are in bytes. Okay. Bytes. Bytes. Okay. And this is also in byte. Right. So the first question, memory is byte addressable. So that means every 1 byte has memory address in physical memory. Every 1 byte has a memory address. Okay. So that means if you take 1 page or 1 frame, this is your address. So every 1 byte or 8 bit has address. Okay. That is how what you get from memory is byte. Sometimes it will say memory is 2 byte word addressable. So that means every 2 byte has address. Remember, word means multiple of byte. Or it will say the memory, each memory address can keep 4 bytes of data. Here it's every memory address can keep only 1 byte of data. Right. So my first question is number of pages. Remember, pages are in the logical side, frames are in the physical side. So in logical side, the total capacity is 4 into 2 to the power 30. And one page can take only 4 into 2 to the power 10. So therefore, how many pages are there? Total divided by capacity of one page. 4 into 2 to the power 30 divided by 4 into 2 to the power 10. 4 to 4 get cancelled. This is indices. 2 to the power 30 divided by 2 to the power 10 is division means subtraction. 2 to the power 20. 2 to the power 20 number of pages are there. Right. So 2 to the power 20. 2 to the power 20. That is the answer for the first question. Number of pages 2 to the power 20. Okay, right. So let's do one by one. So the second part is number of frames. So frames are in the physical side. And here the total capacity is 64 into 2 to the power 20. So therefore number of frames is 64 into 2 to the power 20 divided by number of frames they ask. So therefore one frame is same as one page. That is 4 into 2 to the power 10 byte. 2 to the power 10 byte. So therefore number of frames is, so this is 4, 16. That is 16 into 2 to the power 10. 20 minus 10 is 10. Right? And 16 is 2 to the power 4 into 2 to the power 10. That is 2 to the power 14. So we have 2 to the power 14 number of frames. Right? We have 2 to the power 20 number of pages. Right? 2 to the power 20 number of pages and 2 to the power 14 number of frames. And you can see that number of pages is bigger than number of frames because logical memory is bigger than physical memory. So as a logic, program sees that there are 2 to the power 20 pages. But in reality, in physical memory, there are only 2 to the power 14 pages, frames. So the rest of the 2 to the power 16 pages, 2 to the power 6 pages are in the virtual memory or the secondary storage. If you want to access that, it must be swapped with another one. Okay. So therefore, number of frames is 2 to the power 14. Okay. 2 to the power 14. Sorry, not 2 to the power 14. Yeah, number of frames is 2 to the power 14. So where's the answer? It is not mentioned in my answer. Number of pages are there, number of frames I have not mentioned. Yeah, I will add that into your note, okay? So for some reason I have added that. But you can see here we got 14 bits. So that is how you get it. 14 bits is because of that. Okay, right. Anyway, so let's continue because we are doing it in the proper way. Right. Any questions up to this point? Right. So then number of entries in the page table. Number of entries in the page table. So remember, number of entries in the page table must be same as number of pages, because number of pages are bigger than number of frames. Okay. So if there are 2 to the power 20 pages, number of entries in the page table must be 2 to the power 20 again. So huge, 2 to the power 10 into 2 to the power 10, 1024 into 1024. It's something like million entries. Okay. So that is number of entries in the page table. So now you can calculate the physical address format. Okay. Remember, physical address has 2 parts: page number, frame number and offset. So how many frames are there? 2 to the power 14. So therefore, your frame number must have 14 bits. 14 bits. Okay. So that is physical address. When it comes to logical address, number of frames is, number of pages are 2 to the power 20. To uniquely identify a page, you need 20 bits. So this is 20 bit. And this is 14 bit, because 2 to the power 14 frames are there. So then this is number of offset entries. So that is going to be the same bit. If this is 10, this is also 10. How do you calculate that? Right? Page size is given, right? 4 kilobyte. Right? Page size is 4 kilobyte. If page size is 4 kilobyte, that is 4 into 2 to the power 10 byte. That is 2 to the power 12 byte. 4 is 2 to the power 2. That is 2 to the power 12 bytes in one page or one frame. And remember, it is byte addressable. Every byte has address. So that means 2 to the power 12 entries can be in the one page, because you have 2 to the power 12 byte capacity. That means every one byte has address. So therefore, your page has 2 to the power 12 entries. If you take a page, right? If you take a page, it can have 2 to the power 12 entries. If you have 2 to the power 12 entries, to uniquely identify the offset, you need 12 bits. So therefore, this is 12 bit. And therefore, this is also 12 bit, because offset is going to be the same. So therefore, your logical address format is 20 bit and 12 bit, altogether 32 bit. Your physical address format is 14 bit and 12 bit, altogether 28 bit. So this is 32 bit, 28 bit. So that's it. So finally, we calculate the physical address format, 14 bit and 12 bit. Logical address format, 20 bit and 12 bit. Right? 14, 12, 20, 12. Okay. 14, 12, physical address. Okay. And logical address is 20, 12. Okay. 20, you can see here, 20, 20 and 12. That is logical address, 20, 12. And physical address must be 14 and 12. And see, yes, you can see 14, 14, 14 and 12. So that is physical address. Okay, 14 and 12. Right. Any questions? Any questions? Okay, right. So we'll do a past paper question. So these are not easy. So you need to spend time, again go through this, again think about it until you are confident. And structured paper questions, you can't skip. Okay, you can't skip. Right. So first do the B part. That is nothing to do with. Okay. So we can do the entire question. Fourth question, because this is related to process management. A part. B part is related to file management. And C part is related to memory address or memory management. So you can see full question in second paper A. Right. So you have only 2 questions in structured paper. And this is half of the structured paper from operating system. Okay. This is 2020 paper. Right. First do the A part. A part 1 and 2. Quickly do it by yourself. And take a piece of paper and write the answer just like you're writing it in the exam. And possibly you can post it to WhatsApp group as well. Right. Quickly do it. I'll give you 5 minutes for that. First part. Okay, so let's do this. An operating system uses process control block. Remember we discussed about PCBs last week to maintain important information about each process. So what is the use of process control block? Because so the running processes are given time slots, right? So time slot is given. So take it from run up wait into the running. So then it has to stop it because we need to give it time slot to the another process. So therefore you need to write down all the current state of this process, because after sometimes it has to be resume. Okay, resume. So in order to resume, you must know the current state. The operating system must know the current state. So therefore the PCB has the process number, current execution point, the values of the memory, values of the variables, right? The file, open files, and so on, so that it can resume the task again. So therefore, every running process has a PCB. Every running process has a PCB. If there are 10 running processes, there are 10 PCBs, and it is getting updated every time it is given a time slot and timeout. So then this is updated. And next time when it is started, it first read the PCB and get these information and initialize your registries and so on, and then execute. And after time out, again write to the PCB, and the next process is taken by reading its PCB and so on. So that is how it works. Okay. So these are serious stuff. And these are serious stuff. Okay. Now let's read it. Now let's read it. An operating system uses process control blocks to maintain important information about each process. Yes, correct, right? Read the following scenario and answer the given question. Right? PL starts a spreadsheet program, maybe something like Excel. Right? PL starts a spreadsheet program on a single processor computer. So that is to make your life easier. It's a very primitive single processor computer. Remember, if they have multiprocessors, there can be multi-threading, multi-cores, right? So many things, right? Single processor computer. To use the budget XLS, so this is Excel file that he saved the day before. The day before. He also is running a web browser. Now, parallelly, he is already running a browser like Firefox that he uses to check his email. So while he is already running a web browser software like Firefox, now he has started running spreadsheet like Excel. At a particular time, the operating system changes the process state field in the PCB of the spreadsheet process. So this is the PCB of the spreadsheet process. There must be two PCBs now. One for spreadsheet, other one for the web browser. From running to blocked. So it has changed from, because remember the PCB has the current status also. Running to block. Give one likely reason for the transition. So usually it is not running to block, right? So after timeout, it doesn't go to the block. So remember the process transition diagram we discussed last time. Let me get back to that. So if it is genuinely timeout, it goes from running to ready, but it has changed from running to block. So what is the reason for going from running to block? So there's some input output waiting. So when there's input output waiting, that means user need to do something to proceed. So then the operating system doesn't take it to the ready state, it take it to the block state. Because until the user respond, no point taking it back to running. So the question is, what is the possible reason for it moving from running to block? Right? Running to block. So we have done it. We have done it, okay? Right. So the running, give one likely reason for that transition. So you can just give some reasons like maybe user input is required. Okay. Operating system is waiting for the user action, something like that. Okay. Right. So let's look at the marking scheme answer and see whether it's different from our one. This is 2020. Second question, right? Question. Question number fourth one, right? Yes, fourth one. Right. So these are the possible answers. Spreadsheet process required to read a file. Remember input output, right? It can be user input output or some file. These are possible answers. Just one answer is okay. Spreadsheet process required to write to file. Spreadsheet process doing input, that is input from the user, or spreadsheet process doing output. So that is user input, user output, or file input, file output. So in general, we say input output. So until this is done, there's nothing to process. So that is why I take from running to the block state, right? So correct alternatives to spreadsheet process also accepted. So that means something like this or something very specific which has one of these four features is taken as the answer. Okay, right. So any questions about that? So simply check whether you know the process transitions, the reasons. Right. So second part, when the state of a process changes, running to ready. So that is running to ready means it's timeout, right? Running to ready means it's timeout now. The value of the machine registers are stored in PCB. Yes. So the values of the registries must be kept in the PCB because next time when it resume the processing, right? when it goes back to the running, it needs to initialize those values again and start processing. That is why we say this has some overhead. Why is it important to store them? So now you need to explain that. So when it comes from running to ready, the time slot has expired. So therefore, it has given that opportunity to another program to run, to another process to run. But after sometimes when the operating system resumes the processing, these values must be reinitialized so that it can start from where it stopped. Right. So you can see you have only 2 lines. So therefore, make sure you explain it in a very brief manner. Or you can simply say to resume the task from where it stopped. Right. To resume the task where it's the processing stopped, or not stop actually, where the processing is halted. Those registry values need to be uh, saved in the PC, something like that. Okay. Right. So let's look at the marking scheme answer. So that when the process start running again, or you can use resume, it can start from where it stopped, or you can use the word it can resume where it stopped. Okay, where it stopped. 1 mark for process can start again, resume. Here you can see the word resume is used. 1 mark from where it stopped. So you must have where it stopped and resumed. Right, resume. So those are the important points. If both points are in your answer, you get 2 marks. Okay, you get 2 marks. Right. So the next one. Right. Do the B question 1 and 2. Right. Quickly do. Right. This is 2020 paper. Right. You must have the paper as well. Right. Do the B 1 and 2. I'll give another 5 minutes. I'll give another 5 minutes for you. I don't know whether we did this last time. Anyway, maybe we have done it, but still I want to do it again. Do the 1 and 2. Okay, so let's do it. The block size of a disk is 4 kilobyte, right? So block size is the minimum size that your memory can access. You can't access a particular character in a hard disk or your SSD, right? So we did that. We discussed that, right? So when that block is filled, say your file is 100 megabyte, say block size is 4 kilobyte. So then you need to use one block, another block, another block, another block. So there are different approaches, like contiguous blocks are given. Sometimes you keep a link of that, saying this next block for this file is there. So we discuss those possibilities. Contiguous file allocation, link allocation. Okay. Index allocation, index. Right. So the block size of a disk is 4 kilobyte. The partition of a file allocation table starting from block 300 at a particular time is shown below. Start at 300. Okay. It gives the block of maximum.py file. Right. So this is for the maximum.py file, the file allocation table. Okay. File allocation table. It says it starts from block 300. The file start from 300. So that means 300 block is used for this file. Okay. And note the last block of file is indicated by -1. So that means the last block is 304. So that means this file, for the first part of this file is in 300 because it says, right, starting from block 300. So therefore block 300 is used. So then this says the next block is 303. So therefore the 303 block is also used. It is not contiguous, right? It is not contiguous. So then 303 and 303 says 304. So therefore 304 block is also used and 300 block says -1. That means you don't need to go to another block. This is the end of the file. So therefore this particular file is using 3 blocks: 300th block, 303rd block, 304th block. Okay. So what is the question? Write down the value of an important number that will be stored in the directory entry for maximum.py. Maximum.py. That will help the operating system locate the block in that file. So remember, the operating system must be able to identify, must be able to read this file. So this is for the file. So each file has this kind of a table. But your directory must have entries for the starting point of each file, because starting point is required. So then once you know the starting point, so this table has the next block, next block, next block for that. So therefore each file has this kind of a table, and then you have a big table where you have the file name and starting block, file name and starting block, file name and starting block. So once you go to the starting block, from this block table, you can find the rest of the block. So therefore, in the operating system, it must have this particular entry, 300, because that is the starting point. So maximum.py starting point is 300. For another file, maybe starting point is maybe 303. Oh, sorry, 303 is used by this. Maybe 301 is used for another file. So the answer is 300 because that is the starting point. Okay. So let's see the answer. Oh, it says 301. Why is that? Write down the value of an important number in the directory entry for the maximum PI file. Is it 301? Yes, sorry for that. Okay. Right. So, no, right? Starting point, starting from 300. It says your block start from 300. Sorry. I completely misread it. Actually, the examiner also hasn't given it in a very clear manner. So the question says, your block start from 300, 300, 301, 302, 303, 304, not the file, not the file, okay? So I thought it is a file. So it says, this block start from 300 and goes to 304, okay? So therefore, we need to find out your starting point. Actually, this is sort of incomplete question as well, right? So therefore, you need to find out which one is linked to which one. Right? For example, 301 say 300. So therefore, from 301, you can go to this block, you need to go to this block. And then it says 303. That means from this block, it needs to go to this block. And this say 304, it needs to go to this block. Okay. So therefore, what should be the starting point? Because if you start from here, it goes this. From there, you go there. From there, you go to there. And that is the stop. So therefore, what is the starting point? This is not the starting point because you come into there. This is not the starting from, you go from there. So therefore, what is the starting point? Starting point is 300. So your operating system must keep track of what is the starting point. Because once you know the starting point, you know what are the rest of the stuff and when to stop. So the question is, I completely misread the question. Sorry for that. Write down the value of an important number that will be stored in the directory entry. Directory entry is kept in track of each and every file. Right? So for this file, the directory entry must keep track of the number as what? 301. Because 301 is the first block. From 301, it must go to 300. From 300, it must go to 303. From 303, it must go to 304, and that's it. So therefore, what is the important entry that your operating system must keep track of? 301 for this file. So similarly, for another file, there will be another table like this. For another file, there will be another table like this. So your directory management part must keep track of, for each and every file, what is the starting block. So for this file, the starting block is 300. So therefore, answer is 300. Okay. So the answer is 301. 301. Okay. So that is how it comes 301. So it's a tricky question because the explanation is little bit fussy. Okay. Explanation is little bit fussy. So I thought the file start at 300, but according to the examiner's interpretation, it's about the disk start at 300 and disk end at 304. I think that is what it says, right? Partition of the starting from block 300 at a particular time. Okay. So it doesn't say this is for a file, but for a disk. Okay. For a partition. So therefore, yes. Okay. So therefore, important entry must be 301 to locate this file. Okay. Right. So the next question. Assume that additional improvements are made to maximum PY. So that means you have done some changes to the file. Right? You have done some changes to the file. That result in size becoming 20 kilobytes. Now the file is 20 kilobytes. What changes are needed in the FAT for this purpose? Now remember, each block can keep 4 kilobytes, right? So each block can keep maximum 4 kilobytes. Now how many blocks are used? 1, 2, 3, 4. Maximum is 4 kilobytes. So if it is all 4 are used, 4, 4, 4, 4. That is 16. Right? If it is less than 16, these 4 blocks are enough. If it is 16 or less than 16 kilobyte. But it looks like this is not 16 kilobyte. Now it has become 20 kilobyte. So if it is 20 kilobyte, definitely this can't be -1. This must point to another block. Maybe in this case, of course, the other block must be 302 because that is the available block. So now this must point to something like 302, and 302 may be having -1 because it's 20. 5 blocks are enough. So now you need to explain this. What are the changes need to FAT for this purpose? So your 204th entry will have 302 and 302nd entry might have -1. Or you can just draw this new FAT table. Okay. Entry in 304 changes to 302. 304 changes, 304th entry is changed to 302. And you can see 304th entry is no longer -1, it is 302. And 302's entry must change into -1. 302nd entry change to -1. So that is what is needed. So that means we are using that additional available block also because it is now 20 byte. Right, 20 byte. Okay. Now we have the memory address translation question. Right. So we did the memory address translation topic today. Now you have the page table, page number, and frame number. Present absent bit, whether these are valid entry or not. If it is 0, these are invalid entries. That is why all are 0 for 0. Okay. This is very tough question. Read this question. Read it few times. Okay. Remember, these are structured paper questions. You can't select, right? So second paper, part B, you can select questions, but here you have no other option to do it because you need to do all questions in structured paper. Right? Answer all the questions at this paper, part A. You need to answer all the questions. Okay. Right. So do this as a exercise because you need a bit of time for this. Again, go through the note, right? Maybe you can again go through the recordings of the lecture as well, the class as well, if you have any doubts, and then see whether you can do this. Take your time and do it. And we will do this question as the first thing in the next class. Right. So then maybe we can do one more question or few MCQs, and then we'll move on to our next topic. Okay. in your A-level ICT.